Welcome everybody to the Stats for the Masses webinar, Those Darn Ratios. My name's Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. Today I'm going to present an overview of some common ratios that we see in statistical analysis. The idea for this webinar came after I presented the Bayesian logic webinar, I guess a couple months ago. It was the last one I presented. I had a great many questions from the audience about the likelihood ratio, and I struggled a bit in trying to explain it in a way that made sense to everybody. So today I wanted to use a much stronger word than darn in my title. I wanted to call them other kinds of ratios, but I'll be kind because ratios really are quite useful. And at the end of this presentation is the likelihood ratio, and hopefully I can give a much better explanation to everybody. That's what I'm hoping for. So today's just an overview, but I hope that the information you receive today will give you some ideas and guidance on the usefulness of these ratios and the information they provide as tools for your own studies. And so, as I say in all of our webinars, use what you learned today and apply it in a holistic way. Try to look at that big picture. Don't go get too bogged down into the little details of it. Details are important, but the big picture, always keep that in mind. So I've scheduled 90 minutes for the presentation and the questions. Those of you who have been to these webinars quite often see this slide, but some of you are new, so I just like to let you know a little bit about Omega Statistics and what I do. I own a private practice. I'm in Southern California. Of course, I help people all over the world, mostly in the United States. Medical and clinical research. I do clinical trials, all the phases 1 through 4. I do design and analysis of experiments. I write statistical analysis plans. Of course, I do the analysis and reporting too for studies. So I do both design and the data analysis. I help people with their dissertations. Typically, it's the methods and the results chapters. People who are working on their dissertations do great until they get to the methods, and that's when they hit their wall and call me, and I'm always happy to help with that. I love working with dissertation clients. I do exploratory design, predictive modeling. I help design surveys, and I take on projects of just about any size. I really love working with individual researchers. I like the small startups who are working on maybe testing a new drug, but I do get some work for large corporations and government. And my motto is to provide elegant solutions and effectively applied. So here's some things we'll cover today. We're going to cover an overview of ratios, fractions, proportions, all these things on the top here. And these are things you probably already know, but these are things you'll need to know as we get further on into some of these ratios. We're going to be dealing a lot with probabilities, some rates, some odds. It is just an overview today, so I'm not going to get too much into detail, but I'm going to give you enough information where you can, and some references, and then you can go and look at the references a little bit more and Google things, and you'll learn. But this is basically to give you an idea of what's out there and how it can be used. We're going to look at a lot of things that have to do with the regression. First, we'll look at the coefficient of variation, and that's very easy. That can apply as long as you have a mean and standard deviation. We'll look at correlation coefficients, R squared, also called the coefficient of determination, variance inflation factor, and we'll look at tolerance. These are the three that are really related with the regressions. Then we'll go into more ratios: relative risk, odds ratio, hazard ratio, and likelihood ratio. So we'll go through some definitions. First is the ratio. What is a ratio? It compares values. The big difference between a ratio and a fraction, and in fact, a fraction is a type of ratio, I guess you could say, but the ratio compares values. A fraction will compare one number to the whole. A ratio can compare parts to parts, or can compare a part to a whole. So we have three different ways that we look at ratios. We can do it with the little colon here. So the ratio of men to women in this picture is 3 to 5. Okay, we can use the word 2. We can say the ratio of men to women is 3 to 5, and a ratio of men to women, we can make it look like a fraction. 3 on the top, 3 men, 5 women on the bottom. There is part to part, which would be the ratio of men to women. Okay, if we had part to whole, that would be comparing the ratio of men to everybody. So you would have 3 to 8, because there's 8 altogether. Okay, so different types of ways of looking at it, but it's comparison is the big word you want to use for ratios. As we saw, ratios can be expressed as fractions, but not all ratios are fractions. As I already said, a ratio is a comparison between two or more quantities. A fraction is basically a part to a whole. You have two things. But a ratio, you could have, 3 to 2 to 5. A lot of times when you're I always like to use the baking a cake recipe, but you certainly have more than two ingredients. Or it's a nice summer day here today, maybe later on this evening, or maybe this weekend I'll mix a little cocktail, and it might have more than 3 ingredients. So I'll have 2 parts gin, 4 parts tonic, and 1 part lime, something like that. So it can have more than 2 quantities in a ratio. And then a fraction expresses a number, right? It's expressed as a piece that is part of a whole. Okay, so it is a numerical quantity. Part to part ratio is never a fraction. Okay, a ratio with more than 2 quantities, such as 1, 2, and 5, is never a fraction. And many times part to whole ratios can be a fraction, however, not always. Here's an example. If I have a juice drink, it consists of 1 part juice to 3 parts water. The ratio of juice would be 1 to 3, but the fraction of the drink that is juice is going to be 1 out of 4 because we have 4 parts altogether. We have this 1 part plus 3 parts is 4. So that's the difference. They're not really the same. They are different. Then we have proportions, okay, and that's what we use to say that 2 ratios are equal, okay. So we can use 2 equal fractions, A over B equals C over D, or we can use the colon, we can say A to B equals C to D, okay. When two of the ratios are equal, then the cross product are also equal. So right here we have A over B equals C over D, or written this way, right? Then what we could do is we can cross them. We're going back to junior high, aren't we? So we can do this. We'll multiply A with D, and that's also going to be equal to when we multiply C and B. Okay, so A times D is equal to B to C. And here's an example. Okay, so if I take this number here, 3 and 35, and I multiply them, that's going to be also equal to the product of 21 and 5. Okay, and they both equal 105. Check. So we're good. That's a nice thing about proportions. Percentages. Okay, now we're getting more statistical, right? When we say percent, we mean per 100. 100% means everything. Sometimes it'll be 1 if you're using decimal notation, but I always say statisticians love to keep everything between 0 and 1, right? That's where we work. That's where we live. Mathematicians, we drive them nuts because they want everything absolute, and they want an exact answer, and they need the algorithm and the formula, and they need we go, oh, well, we're between 0 and 1. We work with probabilities. We're guessing all the time, and we never have a straight answer for you. If we knew the truth, you wouldn't need a statistician, So that's another webinar for another time. But 100% means everything, okay? And in statistics, we often look at increases and decreases of things. So here's a couple examples I have. If I make $18 an hour and I just got a raise to $22 an hour, what percentage is that? Well, we would do it this way. We would take what we ended up with where we're at now, and then we're going to subtract this, and then we're going to did I do that one right? This should be 18 here. Oh, yeah, so oops, see that? I did it wrong. 22 minus 18 over 18. 22 minus 18 divided by 18. So that's 22%. Yeah, I'm even happier. Okay, so what you do is you take where you're at now, you subtract where it was, and you divide it by where you were at the 18. Okay, so that's an increase. We can also do decreases. Okay, so the shoes I want, they were $120, but now they're on sale for $90. So what percentage decrease is that? Okay. So I start with the 90, which is where I'm at now. I subtract what they were, and I divide it by what they were. And so I have a decrease of 25%. So I'm happy. I'm happy in both cases, actually. So we use that a lot. Percent and percentage are often used interchangeably, but there is a subtle difference. Okay, the word percent will accompany a specific number, but percentage is often used without a number. Some examples would be, we would say 15% of the 15% of the control group responded to drug B. Well, then we would say percent. Okay, but for percentage, we might say, just in words, a large percentage of the population exposed to the rotavirus. They're a large percentage, usually between 70% and 75%. And in that one, I use percentage and percent in the same one. But as you can see, I said percent when I used the number, but I said a large percentage of the population when I was just talking about percentages. So that's the difference. So when you're writing up results, if it has a number associated with it that you're writing about, use percent. If you're talking about, a large percentage or small percentage, then that's, you wouldn't say a large percent. You would say a large percentage. Okay, this is a fun one. Probability. This is where people get a little scared, but we're not going to get too deep into it today. But I do want to share a few things. This probably is going to be for the preliminary information. Will probably be the biggest set of slides. It's very basic information, but it's going to be enough for today's examples. There's a website link here at the bottom. From StatTrack, and it's an easy read, and it gives you some more definitions of the terms and examples on probability. So if you want to read more, just go right here. Okay. So in statistics, as I was saying, we don't know the truth. We have to make good guesses at it, a real good guess, and we have tools to do that. So every event, person, etc., we measure is different. So we have noise, which is also called error, variability. So if everything was exactly the same, if everybody was the same height or the same weight, then we wouldn't need averages or anything like that. To make our good guess, we need to know how probable or likely an event is to occur within a given situation. That probability, that's what probability is. It's the chance that something will happen. So we'll be talking a little bit about events. What's the chance that event A will happen, right? And it's a probability, it's a guess. And so it's not known for sure. Here's some terminology. Before we really discuss some rules of the probability, I want to go through just a few definitions here. An event means one or more outcomes. So an event could be one outcome, or it could be a set of outcomes. Okay, so think of one outcome as getting heads on a coin toss. Okay, your outcome could be heads or tails, one or the other. Okay, more than one outcome. Maybe we have maybe this set here, A, is even numbers, and maybe well, B wouldn't be odd numbers because then there wouldn't be an intersection, right? But maybe set A is even numbers and B is, even numbers under 20 or something like that. So there could be 2, 4, 6, 8, in this one, and there could be, if they're under 20, it'd be the 2, 4, 6, 8s would be in here, all the way up until 18. Would be in this area, and then here would be all the guys that were still left over. So you could have more than one outcome, is my point on it. We have mutually exclusive, and that's also called disjoint. And when two events are mutually exclusive or disjoint, they can't occur at the same time. So an example would be, if I'm at an intersection, I can't turn both left and right. I can only do one or the other. Okay, that's an example that's pretty easy. Event, okay, and I already discussed that a little bit. That is the thing that's occurring. That's the something that's happening. Okay, so the probability that event A occurs, given that event B has occurred, is going to be this conditional probability. Okay, conditional probability of event A given event B is, you'll kind of see this P. You'll see this written a lot. I'm trying to write with my mouse. I need to get one of those pens, huh? That would be great. A given B. It'll look like that. only much nicer, right? But you'll have this line going down between, you'll have the big P over here. So probability of A given B. So that's saying if B's already happened, now what's the probability of A? And we're not going to do too much of that. We will when we do the likelihood ratios. So a complement of an event is the event not occurring. So the probability that something like, say, the probability that A won't occur, you're going to have something that looks like this. Probability of A, and you're going to have this little prime. We call it prime. It's going to have that little, just a little, like an apostrophe, little prime. Okay. So what that's saying, it's everything that's not A. So let me go ahead and erase this little thing I have here. So everything that's not A, if this is a Venn diagram, so here's A, here's B, and then here's where they share information. Everything that's not A is going to be all the way over in here. This is everything in here that's not A. Here it's sharing with A. A and B are sharing things, so this is still part of A, but over in here would be the complement. So this part, just this area, would be the A prime. Okay. Here's our intersection. That's where both A and B, both sets, are sharing information. Okay. And so that has this little intersection here. Now there's also a union, which is A and union B. And that means whatever you're looking at, your outcome, your event, can be an A or B or both A and B. So it's everything. Everything's a union. Okay. Intersection is just what they're sharing together. Okay. And I used to get confused on that because A and an or. Okay. Typically, when you use or, that's going to be your union, is going to be or. Okay. And then the probability that both A and B both occur, this is our and. And I don't know why it was, but when I was in school, it took me a while to understand that because I just figured and sounds more inclusive than or. But a good way to think about a union is say A or B or both. Okay. And that would be your union. Okay. And then we have dependent and independent. If the occurrence of something happening in A, the event A, does something to the probability of event B happening, then you have dependent. If they're independent, A can happen all at once and it's not going to have anything to do with the probability of B. It won't affect that probability of B. So sometimes you will have some dependent events and sometimes you'll have independence. We like to see the independence quite a bit because it helps us to do a lot more calculations. I'm not going to go through all the rules of probability today. But you know, there are a lot. Conditional is not even really. Sometimes the conditional probability could also be, using dependence. So this diagram, I borrowed it from a place called lucidchart.com, and you can actually build charts, and it costs just your email. I'm sure they have paid plans too, but if you wanted to maybe try that out and build some nifty charts, you could. Do you have any questions on the probability ones so far? Sometimes this is where a lot of questions will come up. Okay, I guess we're doing all right. So far, so good. What good junior high students you are, right? I wasn't sure what people would know or not, so I figured it would be pretty good to go over this. So there are some rules of probability, and I'm going to keep them simple. Oh, yeah, I wanted to show you this. This is when you have the mutually exclusive, okay? And I thought this was kind of cute. So these don't have any intersection at all. There are two kinds of events happening, or two kinds of outcomes. We have people who understand Venn diagrams here and people who don't understand them over here. So you either understand them or you don't. So they're mutually exclusive. So that's a good example of a mutually exclusive types of events. Okay, so there are three rules I just want you to know today. I'm not going to go into all the additive and multiplicative and all the subtraction rules and all that, but three things to know. Probabilities cannot be negative. They have to be between 0 and 1. Okay, all probabilities that are in the same sample space, which would be the collection of all possible outcomes for all of the events, have to add up to 1. Okay, and the probability of an event and the complement of that event also must add up to 1. If I was to go back to the other slide here, the probability of A and the probability of this little area here, the complement of A, if I'm looking at this big sample, this would be my big sample space here. Okay, both of them would be the sample space. So I have A, and here's my complement of A. All these probabilities would have to add up to 1. Okay, so there would be certain probabilities for being an A, certain probabilities for the, maybe the intersection of A, and then certain probabilities for the complements, and they all would add up to 1. So here's a nice little picture. We always deal between 0 and 1. And we're going from where 0 down here, it would be impossible. A 0 means it's just not going to happen. Okay, 100 means you're absolutely certain it's going to happen, 100% guaranteed. Rarely is anything impossible, and rarely is anything certain. It does happen, I would suppose, but not often. So there are some other situations, maybe in between. This 0 would be down here, and the 1 up here. Even chance would be 50-50. Okay, so that's a ratio, 50 to 50. It would be, the percent that could happen and the percent that can happen, right? Or we could say 50%, right? Here, if you got a 1 out of 1 on a dice roll, well, you have a 1 in 6 chance of getting a 1, so you're going to be down here somewhere, 1 over 6, right? Okay, ratio would be I could get a 1 or 1 to 5, right? Because that would be the rest of them. Okay, so again, the ratios and fractions are a little different. And then up here, 4 and 5 chance. So everybody, when you take the probability class, there's always you're spending your time pulling balls out of a hat, rolling dice, and dealing cards. That seems like the statistical probability class is all. It's so, and statistics started with gambling, so it kind of makes sense. We use cards and dice quite a bit. But if you have balls in a hat and you have 5 balls and 4 of them are green, then you have a 4 and 5 chance, and it's pretty likely, right? So your probability is pretty likely that you're going to pull a green ball. Okay, probability is not so likely that you're going to roll a 1, and you have 50-50 chance of, say, rolling a head on a die. Okay, so the higher the probability, the more likely we're going to observe the event. Okay, so I like this little diagram. So I got it from Math is Fun. In case you'll see down here where I say borrowed from, you can go to any of these links and you can see more information. Okay, now we look at rate. Rate is a special type of ratio. A rate involves 2 terms with different units of measurements. A lot of times rate is time. It's over time. It has something to do with time. There's 40 hours per week. 5 miles per hour, 69 cents per 12 ounces. So the first 2 examples above are unit rates because the denominators are expressed in units of 1. So it's 40 hours per 1 week. This right here is a unit rate. And 1 hour, okay? This isn't because there's 12 ounces. But you can take this rates and do some math, and you could figure out what you need to, how much it would be for 1 ounce, or how much you'd need for 24 ounces, right? So that's what a rate is. It's we're going to look at hazard rates, which is a ratio, and it does involve time. Odds. This confuses a lot of people. Odds are a ratio of the number of ways something can occur to the number of ways it cannot occur. Okay, so an example would be the odds of a month being September are 1 to 11. Okay, and that's because, well, September is the 1 month that's September, and there's 11 other months that are not. Okay, the odds of a coin being tails will be 1 to 1 because you can either have heads or tails. Okay, odds are often confused with probability because they both describe how likely it is that an event will occur. However, they're not mathematically the same. Some differences are the probability must be between 0 and 1. Odds can go from 0 to infinity. They can go all, very high. Probabilities are about an event happening, and they're given in percentages, but odds are a ratio and can be stated 2 ways. They can be odds in favor or odds against. Okay, so you can have one or the other on that. Okay, so The mathematical difference between probability and odds are in the comparisons of the ratios. Okay, so a ratio for the simple probability of event A would be this. A probability of A, or the chances of A out of the total chances. Okay, the ratio for the odds in favor of event A, chances of A against. Here's one where we're drawing an ace from a deck of cards. Okay, so the probability of A would be 4. You can get 4 aces out of 52 cards. You can whittle that down to 1 over 13, 0.077, which is 7.7. So 1 out of 13, 7.7%. Okay, so the odds in favor of drawing an ace for odds are 4 to 48, 1 to 12. So a little bit different. Okay, so hopefully you're getting an idea of how that works. Now, odds and probability are mathematically related. You can get one from the other. When we do the likelihood ratio, we're going to take probabilities, turn them into odds, and then take the odds and turn them back into probabilities. So here would be the probability of event A. Okay, it'd be the odds in favor of A, and 1 plus the odds in favor of A. So here you have the odds in favor of A, and then you have 1 plus whatever those odds are. Okay, and now for your odds, using probabilities, if we have the odds of favor of A, then you could take the probability of A and take 1 minus the probability of A. Okay. If we do this, we can look at this. Let's do the using a number of aces that we had. Here was our probability. It was we took our odds in favor of A, which was 1 over 12, and then we took 1 plus 1 over 12, and we get this 0.077. Okay, which is what we had before. Okay, and then we have odds in favor of A. Now we're going to take our probabilities. Okay, so we're going to take the probability of A, which is 1 over 13, which is right here, and then we're going to take 1 minus, right, 1 minus 1 over 13, and we come out with 1 over 12, 1 to 12. So it is the information we did get on the previous slide. So you can use odds to get probabilities and probabilities to get odds, but they are different. Okay. Do we have any questions on some of the preliminary things before I start going into the actual ratios? Okay. Well, good. I'm sure you'll have questions before we're done. But let's go ahead and get started. Here's a nice simple one, the coefficient of variation. Okay, you can use these as long as you have a standard deviation and a mean. It's a measure of relative variability. Okay, so it's relative. So it's, you can take that standard deviation, divide it by the mean, multiply it by 100, and you'll get a number, and you can compare it across groups and such, and kind of gives you an idea of the variability between your different groups and such. So when do we use it? Coefficient of variation is particularly useful when you want to compare results from 2 different surveys or tests that have totally different measures or values. Okay, so an example would be if you're comparing the weight of mice and the weight of elephants. Okay, you're definitely going to have different numbers in both sets, but this will give you an idea of the spread of the weights of mice versus the spread of the weights of the elephants in the data set. So if the sample of mice has a coefficient of variation of 12%, and a sample of elephants has a coefficient of variation of 25%, then you would say that the sample of elephant weights has more variation, because the larger the numbers, the more variation, or the more spread out all your data points are in your data set. So so you would say, since the coefficient of variation was larger for the elephants, they have more spread. So the range of weights is going to be much wider. Now, another thing, if you're comparing 2 different measures, okay, say you're comparing a set of IQ scores for a group and emotional intelligence scores for the same group, okay, they could be measured on different scales, okay. But if you use the coefficient of variation, you can get a bead on which test returned more or less variability for your group. for your group of test takers. They might have been very, very close together on the measurements of IQ, but widely spread out on emotional intelligence, or the other way around, or the coefficients of variation could be rather close in value, and not much different between the two tests. Okay, so they're very useful to do some comparisons. It is standardized, and so that's why you can do it. You're taking a standard deviation and you're dividing it by the mean. So they're unitless. When you hear standardized, that usually means unitless. So that usually means you can compare between different types of tests, different types of groups. You don't need to worry too much about how it was scored. Okay, and as I mentioned, the higher the CV, the greater the level of dispersion and that spread around the mean. Higher CVs are usually seen as being associated with less precision of measurement. And if you think about it that way, if you have quite a few scores on a test and they're all bunched together around the mean very closely, you're going to get more precision on your estimates because you don't have that wide standard error or standard deviation, causing your computations to become wide. And that's usually with confidence intervals and such that we're not going to be covering today. A lot of these ratios do have confidence intervals, some do not. The relative risks does not. It's based on probabilities, but odds ratios, hazard ratios, they do have the confidence intervals. But as I said, this is just an overview, so you can read more about those, on your own. Okay, now the fun stuff. Correlation coefficient. There's lots of types of correlation coefficients. Today we're going to concentrate on Pearson's because that leads right into our R squared. Okay, and because the coefficient of determination is a function of the Pearson's. Okay, but just as an overview, Pearson's correlation is the one that's most known and the one that probably is used quite often. You need to have a linear relationship between your two variables. You're looking at an association between two variables and you want them to be linear, which means whenever you have your x-axis, it will be one variable and your y-axis will be another. That also looks like an x, but that's a y. So you have a lot of little dots. You want to be able to kind of see a line going through them. You don't want to have something that looks like, I don't know. You don't want anything weird. You don't want any horseshoe shapes. Spearman's is for monotonic relationships or ordinal data. A monotonic means it's just kind of moving in the same direction. You're not having this kind of thing going on. Okay, it's not going up and down. Okay, you need to have some kind of a monotonic relationship. Doesn't necessarily have to be linear, but you can't go up and down and up and down. And ordinal, that's when you have things that are ranked. So you might rank something, least happy with as a 1. Likert scales are great for ordinal. That's their ordinal data. So you might rank something from strongly disagree to strongly agree. Okay, and that would be your ordinal. Okay, so that's when we would use Spearman's. Kendall's tau, it measures the proportion of ranks that match between two variables. So it's kind of similar to this, except we're just looking to see how much they kind of match up between the two variables. And then there's interclass correlation. That's used to see how well members of a group match on two variables. Examples would be how well siblings match on genetic traits, maybe how 2 or more judges rank the performance of a group of dancers. And there are so many other correlations, but we're not going to go over them today. But I just wanted you to know that it's not just Pearson's. Pearson's and Spearman's are the ones you'll see the most. But we'll look at Pearson's today. So here's our ratio, correlation coefficient. It is a ratio. It is the amount that x and y vary together, and it's divided by the amount that x and y vary separately. So here, this is our covariance of x and y's in the numerator. So it's a numerator compared to, as you can see, here we're multiplying x and y. Okay, here's our x, and here's our y, and then we're going to multiply them together. Okay, and it gives us the information. Okay, this is the full notation, and you'll see different versions of this in textbooks online and such. There's different ways to write it. Okay, but this is a pretty typical one you'll see. The n's are is your sample size for the x's. and the y's really, because you're comparing, right? So for every x, you would hope you had a y. Otherwise, you can't plot it and you can't look at it, right? So this would be your sample size would be the n, and this is the sum of x times y minus the sum of x times the sum of y. Okay, and down here we have the sample size again, and now we're squaring. We're multiplying it by the squared of the sum of x's. The sum of x's squared. So we want to actually square them and then sum them and then subtract. Now we're summing all the x's together, then squaring that. So it can get kind of confusing. I don't think we need to really go over it too much today, but we take the square root of the bottom, okay, and then we have the top here, and then we get our r. Here's a nice way of looking at it is if you were to standardize your x and y, turn them into z-scores, where they have the mean of 0 and they're the standard deviation of 1, then you can just do this nice simple formula, okay? The z-score for the x values here, z-score for the y value, we're going to sum them up. We're going to sum the product. We're going to multiply them. Then we're going to sum them all up, all the z-scores, and we're going to divide it by the sample size, and that'll give us our correlation, okay? And this is a great reference right here on correlation. So how does that work, right? What is it good for? Well, let's look a little bit more at it. Correlations have values between -1 and 1. The value of the correlation is the correlation coefficient. It's a measure of the magnitude and the direction. Okay, so not only do we have how big it is, like 0.5 or 0.9, but also what direction is it going? Is it going up or down? I kind of wish this graphic went the other way with -1. I always like my negative numbers to be on the left and my positive numbers to be on the right. However, this is a nice graphic otherwise, but it is a measure of the magnitude of the direction and well, the magnitude and the direction, how big it is and what direction is it going. Okay, so right here we have -1. Is a perfect negative correlation, and it goes down. It goes from top to bottom. Here's 1, a perfect positive correlation, goes bottom to top. So when it's positive like this, and you'll rarely see it be perfect, but when you have a positive correlation, see they're all going up in this kind of direction from bottom to top, that means as x increases, y increases, or when you have low x numbers, you also have low y numbers. If you like, say, if you look at this one, well, it'd be down here on the x-axis and very low on the y-axis. If you look at this top number here, it's going to be very high on our x-axis and also very high on the y-axis. Okay. Here with the negative correlation, they go the opposite way. They go top to bottom. And what that means is when your values are going up on one variable, they're going down on the other. So let's look at this one here. This one is very high on the x, but very low on the y. Okay, so it's coming in right about here. Okay, this one here on the top, very high on the y, but very low on the x. So that's negative. Negative means you're moving opposite of each other on each variable, and positive means they're doing the same thing. They're either moving up together or down together. Okay, and then there's different degrees. As you can see, it's a line, then it gets less of a line and less, but you can still see where you could kind of draw lines through these things, right? But as you get smaller and closer to 0, you can't tell anything about one variable by knowing the information on the other, and it's all scattered. You can't draw a line through it. So 0 really means no correlation. Cohen gave criteria for the strength of the correlation, because you might go, well, how strong is it? You know, okay, 0.5, how strong is that? Is that very strong? Cohen said if a correlation was between a 0.1 and a 0.29, that's weak. If it's a 0.3 to about a 0.49, that's moderate, and a 0.5 up to a 1 is strong. Okay, and that's whether it's negative or positive. So that's just a magnitude. So, so that's what a correlation coefficient does. It kind of gives you that measure. I do have some questions. Clarify odds against A. Clarify odds against. Oh, that must have been on a previous slide. I see I haven't looked. Why not just use the standard deviation alone? Well, because Jerry, I'll do that. Isabel, I'll try to get back to you on your question. But Jerry, the reason you wouldn't use the standard deviation alone when you're doing the coefficient of variation is because you're not comparing same things. You're not comparing apples to apples when you're using the coefficient of variation. What it lets you do is you take into account, you divide it by that mean, and it helps you take into account, as I was saying, like if you have an IQ score versus an emotional quotient score, maybe your IQ score is, it's going to be what, from 60 to maybe 160, something like that on a scale. And your emotional intelligence score, that might be scored from 0 to 20. So there's not really going to be a good way to just look at the standard deviations. You want to take that mean into an account too, and then multiply it by 100 and get some kind of number. What it allows you to do is to look at the at different measures. And can you also have a p-value for the Pearsons? Jerry wants to know. Yes, you can. When you run a test, right? And you would, with these correlations, you would run a test. You would compare x against the y, right? Your two variables, and you would come out with a correlation and a p-value. Okay. So yes, it would give you that measurement of effect and also a p-value. Okay. And we're not really going to go into p-values too much today, but yes, you would get them with a correlation. Is it possible to have a strong correlation but a weak p-value? Yes. Yes, it is. Mostly that's going to be when you have too small of a sample size. Well, yeah, sample size would have a lot to do with it. Let me think. If you had a strong correlation and a weak p-value, yes, you might not have enough power in your study. So maybe you only have a sample size of maybe 20, and you get a really strong correlation of like a 0.6. Is fairly strong, and you say, well, in most studies that would be great, so that's a strong effect, that's a strong correlation. But since you had such a small sample, you might get a p-value of like 0.2, which is not significant, and then you say, oh darn, I should have pulled a bigger sample. I know Pearson's correlation, typically to have that medium effect, to see an effect of like a point, the bottom of the moderate effect, like a 0.3 or so, you need about 84. So 84 subjects. So if you only had 20 or 30, you're going to miss it. You might have a correlation of a 0.4 and you just don't have enough. It's called underpowering a study. So Isabella wanted me to clarify odds against A. Okay, so odds against would be, just turn this around. You would have the chances against A to the chances for A. So that would be your odds against. You would just turn this right around. Okay. Let's go forward. All right, so we have our correlations. So we know how those work, and so those are great. That's a ratio. And I think Jerry asked whenever he registered for the webinar, one of his questions was, is R squared a ratio? Well, it kind of is. I wanted to show it with the correlation, right, because it is important. And I think it's something that we really would want to look at. But here's our ratio, and we squared it. So I kind of cheated a little bit, Jerry, but it's a squared ratio, okay? And so the coefficient of determination is the Pearson's correlation coefficient squared. And it's actually what it turns into once you square it. It's the ratio of explained variation divided by the total variation in a regression model. Okay, so since it's a squared ratio, the value of R squared is we're not going to have negative anymore, right? Because we squared it. So our value is going to be between 0 and 1. Now you could get a negative number. There are times I've run models, I've ran a model and it came out with a negative number, but that either means your regression model is not very good, okay, because the R squared compares the fit of the model you made with an intercept only model. And what that means is that it's going to compare what you built in your model with just the mean of the dependent variable. And so it could be just that your model's not a very good fit at all. It can also happen when you don't include an intercept in a model. Okay, a lot of times people, usually you do include, a lot of times we will include that intercept. Sometimes you'll see it called a constant term. We'll include the intercept. We just disregard it, but we want to include it in the model. And then it could be possible that your model's doing even worse than just using your sample mean for y if you don't include that. So in other words, a negative R squared means your model's not a good fit. Try to make some adjustments. Okay. A question I would have would be maybe when would you not use an intercept in the model? And I would say the best time, the only time you should do that is when you're sure that that intercept is going to go through the origin. If it's going to go through that point where x and y are 0, then that would be models maybe that have dummy-coded predictors, all dummy-coded, and so it's possible for them all to be 0 simultaneously, okay? And when they're all 0, the dependent y will be 0 too, okay? The dependent variable will be 0 because everything's 0. Models with all standardized values would all have a mean of 0. They can also sometimes be built with no intercept, but usually play it safe unless you have a good reason for not including that intercept. Now, sometimes you'll include an intercept and you'll still get a negative r squared. A lot of times you'll get a negative adjusted r squared. Now I'm going to show you adjusted in a little bit, but that'll happen too. But typically, anytime you see a negative r squared or adjusted r squared, it probably means your model's not going to be very good. And it's no better, basically when I mean not very good, it's going to be no better than just knowing what the average of your outcome was. Okay, you don't need all those predictors in a model. You could just take your average outcome score and it does fine compared to what you built. Right, so you don't want that. You want to build something better, right? You want to build things that a model with good predictors that are going to change that outcome of y, so from the average, right? So an r squared is 0. That would mean that the dependent variable cannot be predicted from the independent variable, of course. R squared 1 means that the dependent variable, which is usually, we call that y, can be predicted without error from the independent variable. It means a perfect fit. Rarely happens. I've never seen it happen. Yeah, even there, I've even built a model once where I had height and weight and BMI was the outcome, and it still was not a perfect fit, right? So it was close. I think it was 0.9 something. It was close. But the higher your values of r squared, it means the more your predictors are contributing to your outcome. So if you have an r squared of, say, like a 0.7 or 0.75, that would mean 75% of the variability or 75% of that outcome, your y variable, can be accounted for by the predictors you put in your model, and that's very, very good. In social sciences and psychology, you'll see oftentimes r squareds that are very, in my opinion, might as well be 0. You'll see r squareds of 7 or 10%, 0.07, 0.10, but that's very good for that kind of research. If you have the type of research which is a lot of times in sociology and psychology and such, where people are doing self-assessments, they're taking surveys, you'll get usually low r squareds. Okay, that doesn't necessarily mean your model's bad. You got to think about your research context. If you're a psychologist and you get an r squared of 0.15, you're going to be happy. Okay, if you're trying to fit a model on survival rates and you get some kind of like a Cox regression or something, you get an r squared of 0.15, you're not going to be very happy. Okay, so it really depends what field you're working in. So here I have some output. So it might make it a little bit easier to see where you would see an r squared. This is SPSS. I use it quite a bit. It's very user-friendly. I think it's coming on board more and more. A lot of people in academia use it, not so much in clinical research. Everybody's still stuck on SAS, and I think R might actually be going to take that over because R is free. But I do see more and more with SPSS, and I like it. I think the output it provides is very easy to show and explain. But I ran a regression model, and what I did was I had a dependent variable was the total emotional intelligence score, okay? And it was from an EQ type of survey. I'm not sure what the name of the survey was. But it was an emotional intelligence survey, okay? And it had a bunch of different predictors like happiness, optimism, probably had about 13 different predictors. But I only included social responsibility. I included the gender of a person, and I included the age of a person. Okay, so and then I had a sample. I think it was 250. 250 people. And so I took social responsibility scores. I took whether they were male or female, and I put in everybody's age, and then those were all my predictors, and then my outcome was this total EQ score, which is the emotional intelligence score. So I wanted to know, how well did these 3 predictors contribute or explain the emotional intelligence score? I was hoping it would be high. So what I would do is I would first look at this regression output. I would look at the model, and I say, oh, yay, it's good. when it's a p-value, is the sig is the p-value, and SPSS calls it sig. So the p-value is less than 0.05. So yes, the model's good, which means that the predictors as a whole contributed more to that outcome of emotional intelligence than just knowing the average emotional intelligence score for 250 people. Okay, so the predictors are contributing something. So now my next question is, well, how much? How much did it account for? Well, here's my R squared right here, 0.642. Very good. That means they accounted for about 64% of the outcome. And that means that there's some out there, it's 1 minus 64%. So if you had an R squared of 64%, that would mean there's still 36% of the variability in the emotional intelligence score that we didn't account for in the model. Okay, so it's out there floating around somewhere. We don't know what the variables are. It might be some of the other variables in the data set, right? But you're never really going to get, as soon as I say never, somebody will, right? But typically you're not going to get, that's a great R square. You're not going to get much higher than that. I guess you can, but I'll tell you a little bit more about it in a bit. But the more predictors you put in the model, the more you'll increase this R square. So you want to be careful about that. But there's other ways you can find it here. I mean, this just gave it to us. But if I wanted to, I could take, to find the R square, I could take some of this output, or if it doesn't, if for some reason your software doesn't give it to you, which it should, but if it doesn't, you can kind of take this ANOVA table and do some work. You can take the sum of squares for the regression, which would be this number right here, and you can divide it by your total sum of squares, which is this number right here, and you take that fraction and you divide it by 1, and you'll get the same answer. And then here's some other ones here. So this is the same one here, and you can also do the 1 minus this the SSE, the sum of squares for your residual, which actually this is sum of squared error, which is the same as this one right here, sum of squares residual. Residual and error are the same thing, okay? And then you're still going to divide it by that, okay? So it says RSST. I know this one works. So this one here, sum of squared, I'd like to try that one because the numbers are different, right? So I would think I would get a different one here. I'll check this, but I know this one's right. I checked that one. Okay, so there are different things, different ways of computing it. There's not just one way, and one way, and it might depend on the kind of information you're using. What's your data look like? What kind of model are you using, as far as what you're going to use to compute your coefficient of determination. So let's go to the next slide and see what we have. The adjusted R square. Okay, so I mentioned it a little bit. R square is great whenever you just have one predictor and one outcome. You don't need an adjusted R square. Okay, adjusted R square is what you're going to use when you have more than one predictor, which is what we should in this case because we had 3, right? We had age, we had gender, and we had social responsibility. So we had 3 predictors. A problem with a regression model is that you add more predictors, it's going to just increase the R square just because you put more into the model, okay? One of my things I usually say is that if you put in the kitchen sink, the model's going to improve. So, like people say, everything but the kitchen sink. Okay, well, I'm going to throw in the kitchen sink. I'm going to throw in social responsibility. I'm going to throw in gender. I'm going to throw in age. I'm going to throw in the kitchen sink. I'm going to throw in my, my dog's name. I don't know, things that you don't need, that have nothing to do with emotional intelligence. But you could throw a lot. You could throw in 20 predictors. Your R squared, this guaranteed to go up just because you put in a lot of predictors. Okay, so in a multiple regression model, it's good to look at this adjusted R square, and what it does is it's going to take into account the number of predictors you use, and that's going to be this term right here, K. Okay, so what you'll do is 1 minus all of this, but your K is in here, so this would be 3 in this case. Okay, so if I did all of this, I would come up with the 0.637. Okay, the adjusted R squared is less than the unadjusted R square, of course, because we're subtracting this out. So you'll see an R square. When you write your reports, you'll probably want to put both in when you have a multiple regression. You'll say the R squared was this, and the adjusted R square was this. So you can see it accounts for those predictors in the model. Okay, and that just keeps you from The reason we do that is because you don't want to unnecessarily inflate this and make it look better than it needs to be. Let's be conservative, right? Um, don't be a cowboy. um, be conservative. I would rather err on the side of caution than to say I have something great and terrific then fall short later when the product goes out, or so somebody comes along later with another analysis and shows that it was more closer to this than this. And in this case, they're not all that different. They're both very strong. I'd be happy with either of those numbers. Okay. So that was the coefficient of determination. Do we have any questions on that one? And I think I answered Jerry's question. Jerry said, what does the adjusted R squared adjust for? Did I answer that for you? You might have asked that before I talked about it. No, you missed it. Okay. What it does is it adjusts for the predictors in your model, Jerry. So this K right here will be the number of predictors. So in this case, we had 3 predictors in the model. So this goes into the formula and it adjusts that R squared down. And the reason is like I was saying, if you put the kitchen sink in the model, if you put sometimes your R square is going to get inflated the more predictors you put in. So it's unnecessary inflation. So what that does is it adjusts it down to a more reasonable, conservative estimate of what your predictors are doing to that outcome, how much they're contributing. Because sometimes, you want to adjust for that just because of the fact that when you build a regression model, the more predictors you put in, the higher that R squared goes just because that's the way the model is. But isn't the inflated R squared legitimate if it actually predicts? Yes. Yes, it is. It's legitimate, but you have to control for the model the number of predictors. So that's why you use the adjusted R squared. So if I put in 20 predictors and they were all significant, I guess you could say that the R squared would be fine, but we like to use the adjusted R squared just to help be conservative, okay? Because we know as statisticians that when you add more terms into that model, more predictors, you're just going to increase the R squared, okay? But if they are all significant and such, then yes, I guess you could say that. But I would report both. And like I said, they're not that different. Okay, we just want to make that little adjustment. But there were many, many years ago before somebody came along with the adjusted R squared, people just reported the R squared. So I'm not saying it's never been done, but you just want to be conservative and you want to be thorough and include both when you have more than one predictor. Okay. Oh, we're running out of time. I don't want to go too. Boy, did time go fast, huh? Talking too much. All right, variance inflation factor. It detects multicollinearity in multiple regression. I thought I would throw this in since we were talking a little bit about the regression. And here is the ratio we're going to use for that. It estimates how much of the variance of a regression coefficient is inflated due to multicollinearity. They're usually calculated by software as part of the regression. It comes out in the regression. If you see a VIF column as part of the output, that's what it is. They're calculated by taking a predictor, and it's being regressed against every other predictor in the model, and this gives you R squared values, which can be plugged into this VIF formula. Okay, so each predictor is being compared to the other predictors, and that's what this I is. This is the R square for a predictor when it's been compared to some of the others. Okay, and so you have this formula. Okay, so the I represents each of the predictors you're looking at. So let's go to the next one. So is the VIF and odds? It's a comparison, right? It's one, and it's not a part being divided by a whole, right? So this is actually, it is a type of ratio. It's a one, one being compared to 1 minus R squared. So it is a type of a ratio. Yeah. Okay. So I'll show you some more here on the output. They range from 1 upwards, okay, for variance inflation, and right here it is in the output. Okay. What I did here was I ran it the total emotional intelligence score as my dependent variable. So we have emotional intelligence as our outcome, and our predictors were going to be happiness, optimism, and something called general mood, which is actually a combination of some of the different terms or some of the different predictors. So actually happiness and optimism are are used to compute general mood. So I just did this just to show you what would happen. Since happiness and optimism are actually part of the general mood score, you're kind of putting in some of the same thing in a model, or you're putting in too much. You either could do a model with just the general mood score and not put in happiness or optimism, or you might want to take out general mood and look at happiness and optimism separately. Okay, but whenever you do things like that, this is when you're going to get to multicollinearity, because that just means a higher correlation, a very high positive correlation. And we know when you have a high positive correlation, that means that both of your predictors are doing the same thing. So it could be that, we don't, if happiness and general mood are basically you're getting the same kind of scores for both, and they're assessing the same thing, you don't need them both in the model. Okay, you only need one. And that's what you have here. That's just what this tells you is the variance inflation factor. A rule of thumb for interpreting them is if you have one, you don't have a problem here, that you want to see ones, and you want to see what you really want to see are things that are less than 10. Some people say one is not correlated. Between 1 and 5 is moderately correlated, and that's fine. And anything greater than 5 is highly correlated. Other people say, hey, 10 or less is fine. Okay, and what's known is that the more it increases, the less reliable your regression results are going to be. So I say in general, if it's above 10, that indicates a high correlation, and that's cause for concern. But I've seen some people say a conservative level of 2.5 or more. And again, it depends on the context. What's your field of study, okay? Sometimes variables are highly correlated, okay? So just because you get this doesn't necessarily mean you have to pull it out of the model, because sometimes your variables are highly correlated, but they're both important to the model. Maybe they're highly correlated, but they are indeed assessing different things, okay? So if the variable's important and the information it contains is not closely related to another variable, like it's not assessing the same thing as another variable, then I would make an argument for keeping it in. So sometimes it's no cause for concern. You can get a high variance inflation factor by including products or powers of other variables in your regression. Like if you have an interaction term, say if I had happiness, optimism, and then the interaction of happiness times optimism, I might have a high variance inflation factor. And I probably wouldn't want to include that interaction term, or I might want to include it on a second step in a model, do a step model, something like that. So there are things you can do rather than just take out the variables. Just because you have a high VIF doesn't mean you are obligated to take it out, but you want to think about why it's happening and what you want to do. All of these are very high for all my variables because, as I said, optimism and happiness were used to compute this. Okay, so I want to go back and look at that a little bit more. So I removed that composite variable. Okay, and I just kept optimism and happiness. Okay, and now this looks really nice. 1.67. These ones look good. I'm happy. Okay, and I didn't need that other variable. My R squared's still good. Okay, might have went down a little bit, but not too much. Adjusted R squares, very close. Okay, because we only had 2 predictors. Okay. Another way to check would be this tolerance value. Tolerance is 1 minus R squared. It's like the anti-R squared. It's where the R squared value is obtained by regressing again the predictor onto remaining predictors in the model. So the computer does it for you. I'm not going to show you today. But various recommendations for acceptable levels of the tolerance is a value of 0.10 is the most common. You want it to be less than that, 0.10 is the minimum that you want, not less. You want it to be more than 0.1. Okay. Some people say that you would like a minimum value as high as 20. 0.25, things like that. But tolerance is said to be the opposite of this coefficient of determination. In that sense, tolerance is identical to what's called the coefficient of alienation. And it's basically you have R squared, and the coefficient of alienation is 1 minus the R squared. Coefficient of alienation represents the proportion of variance in the dependent variables that's not accounted for by the predictor. So when I was talking about the latent variables that are out there floating around, that's what your coefficient of variation, or I'm sorry, coefficient of alienation, okay, is showing us. I wanted to show one other neat little thing here. You might have this R squared value, okay? But you're saying, okay, the two predictors as a whole are contributing about 73% of the variability to emotional intelligence outcome, okay? But then your question would be, well, which one? They're both significant, right? They're both less than 0.05. Well, which one's contributing more, optimism or happiness? Well, what you can do is you can use something called a semi-partial correlation coefficient, okay? But it's pretty easy. Don't use the partial column. Use the part column in the SPSS output. It's confusing, but what you would do is you would take each of these predictors and you just square them. So for optimism, I have 0.414, and I'm going to square it. And so I get a number of 0.171, okay? Now this one here, 0.314, and I'm going to square it, and that comes out to 0.098. So this one here explains about 17% of the variance. Unique variance, okay? So optimism is contributing uniquely 17% of this R squared, okay? And happiness is uniquely contributing about 10%, 0.098, right? So about 10% uniquely contributed by happiness. So optimism is contributing more than happiness to the outcome of total EQ or your emotional intelligence. So I love that. I love knowing that. So I thought I'd share that with you. Okay, so I'm going to go on and then I'll answer some questions if I can at the end because I wanted to go through this and I already see we're going to run over. So we have relative risk, okay? It's a risk ratio. It's called the relative risk or the relative risk ratio. It compares the risk of an event. Maybe it's a disease, injury, it's a risk factor of some kind or death among one group with the risk among the other group. Okay, so it's going to compare. This is the one I said compares two probabilities, so you can't really get confidence intervals. So it'll compare the probability of an event in one group compared to the probability event in a second group. Okay, it's very similar to an odds ratio, but this relative risk is calculated with percentages, and the odds ratio is going to be calculated using a ratio of odds. So that's the big difference. Well, there are some other ones too, but we'll go through that a little bit later. Relative risk values are greater than or equal to 0. If they're equal, if it's 1, then it's a neutral result, which means you have equal chances of the event occurring in both groups. If it's 0, it means none of the cases in the numerator group had the event, which makes sense because it'd be 0 in the numerator. If it's greater than 1, it's an increased risk for the numerator group, which means that there's more of a risk to them. And if your risk ratio is less than 1, that's a decreased risk for the numerator group, which means an increased risk for the denominator. Okay, so these are some values to know on that. Yeah, it's going to divide the risk, basically, probabilities of risk. Often a group of primary interest is labeled the exposed group, and a comparison group is labeled an unexposed group. So you'll see that quite a bit. You can even, use demographic factors like gender and such to figure that too. But those are why that's used. Okay, here I have a potato salad example. You'll see this online quite a bit, and I think it's kind of easy to get the point across. We want to see if those exposed to potato salad, because I said exposed and unexposed, right? So we want to see if those exposed to potato salad had a greater risk of getting sick than those who were not exposed to potato salad. Okay, so they ate it. Who got sick, right? The risk for each group is called the attack rate, and it's this value right here. Okay. So we have that your attack rates would be that. This would be for the group A. For group B, it would be C divided by C plus D. Okay, would be your attack rate for group B. I just put A. I put only for group A. Okay. So here's our formulas. Okay. So here's the probability up here on top for group A. And here's the formula that we're going to find the probability for group B, and we're going to come out with our numbers, and we're just going to take the 5570 over 70, and we can multiply it by 12 over 2, or we do it that way. This is the number we come out with, 4.71. Okay, and you can see right here, you had a lot of people that got sick off of the potato salad, right? So you can just eyeball it and go, wow, it looks like there's a big risk for eating that potato salad. Those who ate the potato salad then had a 4.71, they had 4.71 times the risk of getting sick than those who didn't eat the potato salad. So we can also say that those who ate the potato salad had a 371% increase in risk. What we would do is if it's above 1, we're going to take the number and subtract 1 from it, and that'll give us percent increase in risk, okay? Another way we can say it is that those who ate the potato salad were 4.71 times as likely to become ill compared to those who did not eat the potato salad. Now, in each of those ways I said it, we always had that comparison group, right? So you can't just say that the people who ate the salad, potato salad, had 4.71 times the risk. You have to say compared to what? Compared to the people who didn't eat it. So always remember that. And don't just say more risk, right? You have to say times the risk, okay? Don't say those who ate the potato salad had 4.71 more risk of getting sick than those who didn't. Because remember, we're using ratios, so it's times the risk, okay? So we want to make sure that we say it that way. I'm a real stickler for saying things the right way. And I don't always. Sometimes I make my mistakes too, but it's a good thing to know. And a lot of these things I learned the hard way, so you get to hear them from me. Relative risk is a simple ratio. Many folks tend to use the terms more or less. Okay, like I was saying, it's not correct. Because it is a ratio and expresses how many times more probable the outcome is in the exposed group, the simplest solution is to incorporate the word times the risk or times as high as in your interpretation. So if you're interpreting a risk ratio, you're always going to be correct by saying those who had, name the exposure, had a relative risk, put the times the risk, compared to those who did not have the exposure. Okay, you're always going to be safe saying it this way. Or you can say times as high as, okay? And like I said, remember to include both groups. You have to say times risk as compared to who, what, right? Okay, so now the odds ratio. I'm going to run through these and then I'll ask the questions because I want to cover them. And then those who want to stay longer, maybe we can answer some questions. And then the questions we don't get to, I'll answer, when I do my follow-up email. Okay, so odds ratio. It's one of my favorites. It represents the odds that an outcome will occur given a particular exposure or treatment compared to the odds of the outcome occurring in the absence of the exposure agreement. So here we're saying the odds, right? So now we're dealing with odds again. So it's good. Odds ratio, I always say it's like a ratio of ratios, okay? So because the odds are a ratio for one group and you're going to compare it to the odds of the other one, okay? This is most commonly used in a case control type of study. You'll see it all the time in logistic regression models, always reported with logistic regression. We can make use of this two-way frequency table here to study the odds ratios, to figure the odds ratios. I guess I should say what a case control study is for those who don't know. You have two groups, all right? So one group has the outcome of interest and the other doesn't. But you're going to look back in time. So you're not going to randomize them into a study and then give a treatment to one and not the other. What you're going to do is they come in already in their groups, basically. You already know what group they belong to, and then you're going to look back in time and you're going to compare the frequency of exposure. So in this case, it'd be like the people that came, they already ate the potato salad and they got sick, right? So, okay, this person came in sick and this person came in well, okay? So that's how they came into the study. Now we're going to go back and we're going to say, okay, who ate the potato salad? Okay, so we're going retrospectively back. Okay, if we did an experimental type of study, we would put people randomly into two groups, feed one group potato salad and the other group not. Okay, so that's the difference. They're coming in sick and we're going, all right, who ate the potato salad? Odds ratios, if they're more than one, if they're equal to one, basically that's a ratio of one. Basically means there's no difference, right? If you have a fraction, it comes out 1. That means that both groups were the same, or their numerator and denominator were equal. So if you have an odds ratio of 1, that means that the exposure doesn't affect the odds of the outcome. You have equal odds, okay? If your odds ratio is greater than 1, then that means the exposure group is associated with higher odds of the outcome. And if it's less than 1, that means your exposure group is associated with lower odds of the outcome when compared to those who were not exposed. So, the people who ate the potato salad here, if they had a bigger odds here, then that would mean that they were more likely, they had a higher odds of getting sick, okay, as compared to the other way around. Okay, so, and then a lot of times you'll see these tables. So here's exposed and not exposed, and here's the outcome. Here's a positive outcome, or the outcome you're looking for, the outcome you're investigating, versus they didn't have the outcome, okay, that you wanted. And this is if they were exposed to the treatment and not exposed. And then you have your little letters here. And the reason they are there is because on the next slide, I'm going to show you some more on how to use them. Okay, so again, A is the number of exposed cases, and they had this positive outcome. B is the number of exposed non-cases. So they were exposed, but they didn't have the case. Okay, their outcome was negative. Okay, C is the number of unexposed cases. So they're not exposed, but they did have the outcome. They came in sick, but they weren't exposed. And D would be the number of unexposed cases. So unexposed non-cases. Okay, so they weren't exposed and they didn't get sick. Okay, so yeah, these are the ones that, they didn't eat potato salad and they didn't get sick. Okay, so here's the formula for the odds ratios using that type of table. You have this ratio up here, A to C, and in this one here, B to D. You can do a little math, and then you can do this, you can multiply, right? Because what you do is just turn this around. And then so what you're going to do is multiply these ones, and then you're going to divide them by the product of C and B, okay? So in other words, you'll have it this way. You're going to have the number of exposed cases times the number of unexposed cases right here, and you're going to divide it by the exposed non-cases and multiplied by the unexposed cases right here. And C was the unexposed. Yes, this should be unexposed non-cases. Yes, this should be unexposed non-cases right here. Sorry about that. I'm going to change my slides. So that's your formula. Well, what are these good for? How does that work, right? Let's look at the potato salad. So using our formulas in our little table, here are the people that ate potato salad and got sick, 55. Ate potato salad, didn't get sick, 15, so on and so on. These are the people that didn't eat it. 2 still got sick, right? 10 didn't. So we do our little formulas, right? We multiply these two, and then we multiply these two, and we divide these by these. We get 27.5. Well, that's a lot different than that 4 point something we got. What was a 4.71 and 27.5? So a lot of times people will confuse risk ratios and odds ratios, but obviously they are not the same thing. We're not getting the same numbers. The conclusion we're going to get from this is those who ate the potato salad had 27.5 times the odds, not times the risk, but times the odds of becoming sick than those who did not eat the potato salad. Okay, so there is a way you can interpret this into being more or less likely. A lot of times people do not like looking at this 27.5 times the odds. They're like, what in the world does that mean? So sometimes what you can do is it's similar to what you can do kind of with the risk ratio. I have that 20. If I have a number of an odds ratio, if it's bigger than 1, what I can do is I can subtract 1 from it and then turn it into a percent. Multiply it by 100 and turn it percent. So in this case, I would take the 27.5. I would 27.5. Oh, this is horrible writing. And I'm going to subtract 1. So I'm going to get 26.5. And I'm going to multiply it by 100, which is going to move that over. So I'm going to get something like 2, 6, 5, 0, right? That's my new percentage. So what I could say is that those who ate the potato salad were 2,650% more likely to become sick than those who did not eat the potato salad. Okay, so that's a lot. Big odds there. The other way you can do another way to do it is if this is less than 1, if your odds ratio is less than 1, what you do is subtract it from 1, and that will give you the percent, and multiply it by 100, right? And that'll give you the percent less likely. Okay, so if I had like something that was a point, I'll make it easy. If it was a 0.50, I would subtract it from 1, right? Which would still give me 0.50 because it's the other half, right? Multiply it by 100, So I would say that if I had an odds ratio that was 0.50, I would say that the group that I was looking at was 50% less likely, percent less likely, 50% less likely. Okay, so that's a nice little trick you can do with odds ratios, and you can watch this again and do some math yourself because you will get the recording. Okay, risk ratio is 4.71. The odds ratio was 27.5. Very different. If the risk of illness was the same in both groups, both your potato salad eaters and non-potato salad eaters, then the odds in two groups would be equal, and both the risk ratio and the odds ratio would be 1. Okay, but those who ate the potato salad had 4.71 times the risk of getting sick and 27.5 times the odds. Okay, risk seems a lot easier to understand because this makes a lot more sense than the 27.5. The 4.71 makes much more sense. It's simply the ratio of the probability of a bad outcome under treatment to the probability of a bad outcome without treatment, right? So why do we need the odds ratios? Well, because logistic regression is great for using odds ratios, case control studies, and rare outcomes. Logistic regression, the reason we like odds ratios, often we want to do more than just compare two groups. We want to maybe fit some models where we can put in some other predictors like age, gender, optimism scores, right? We're not just looking at, the potato salad eaters and the non-potato salad eaters on whether they got sick. Maybe in addition to them eating potato salad, we would like to know, did females get sick more than males? Or was age a factor? Did older people get sick? Did the babies get sick? Not babies wouldn't be eating potato salad, but there could be other factors that have to do with that illness, right? So logistic regression allows us to run a regression. It gives us odd ratios for each of the predictors, and so we'll use that, okay, rather than risk ratios. Case control studies, individuals are going to be selected into study with a probability, which depends on whether they experience the event of interest or not. Okay, so they're particularly useful for studying diseases which occur rarely, but a case control study might attempt to enroll all those who experience the event of interest in a given period of time, along with a number of controls, right? So they already know if they got sick or not, and they're bringing them in, and those controls didn't experience the event of interest. So in a case control study, the proportion of cases is under the researcher's control, right? So you're only going to bring in so many that got sick, and then you might bring in a number of controls, but you're controlling how many people are coming in. You're not doing an intervention and then looking at it. You're already bringing them in, and you're setting how many people you're bringing in. So in particular, the proportion in the study is not representative of the incidence in your target population. It's just people that came in. So you're just looking at people in the study. So as a consequence, you can't estimate risk or risk ratios from case control studies. Okay, at least not without external information. Now, if you had some information on the prevalence of how many people get sick from potato salad, then you can incorporate that in, but odds ratios, it's great because it can still be validly estimated with a case control design because there's a symmetry property. If I was to take this and turn it around so illness and no illness was here, and whether they ate potato salad or not was here, and group them in their right groups and do the math, I'd come up with the same number. You wouldn't do that with the risk ratio. It wouldn't be the same. So that's a nice thing. It allows you to, you can turn it around. So that makes it very, very useful. Okay, so there are reasons for that, that you want to maybe use it. Rare outcomes. Risk ratios and odds ratios are very, very similar when the event is rare, but as it becomes more common, or the outcome when it's not rare, the two measures go, they're very different, okay? So I would say the takeaways are we can calculate relative risk if we can estimate the probabilities of an outcome in each group. So we have to be able to estimate those probabilities of the outcome, right? So you have to kind of know that. We can't do that in case control studies because they're already coming in with the outcome, and we're setting up our study like that, right? We're kind of doing it retrospectively, right? So we're not doing it forward thinking. However, we can calculate the odds ratio even if we don't know the probabilities in each group. Okay, so that's the reason that we need to use those odds ratios. So now we have hazards. Hazard ratio is a measure of an effect of an intervention on an outcome of interest over time. And it's a rate, okay? So it's often confused with the risk ratio, but they are not the same. The main difference is that the risk ratio only cares about the occurrence of an event by the end of the study. So we did something, they got sick on the potato salad, and we're just looking at them at the end. But the hazard ratio is going to take into account both the number of the events and the timing of each event. And in this case, an event is going to be, it's usually a survival curve, so it's going to be death. It might be, it could be happy things too, like, how long did it take for a person to graduate? That would be an event. How long until a person got promoted? That's an event. So they don't necessarily have to be sad things, but often in a lot of the literature I deal with, it is kind of sad survival, like how long did they survive before they died. So and it's just a ratio of hazards. And I'm not really going to go into how the hazards are computed. You can use your survival analysis options in your software and it will compute it for you. But here, it's what it is. It's the hazard in the treatment group divided by the hazard in your control group. And that's typically what you have. You have some group that you've given a treatment for, and you're wanting to see if they survive longer than the people in the control group. Okay, hopefully they will, and then you can say that if it's significantly so, then maybe, your product, your drug, or whatever you did is useful. Okay, hazard ratios that are 0.5 at any particular time, what that means is that any particular time, half as many patients in the treatment group are experiencing an event compared to the control group. Okay, half as many. Okay, so that's actually pretty good. If it's 1, then at any particular time, the event rates are the same. Okay, and if you have a hazard ratio of 2, at any particular time, twice as many patients in the treatment group are experiencing an event compared to the control group. We don't want that. So we kind of want our numbers to be less than 1. We want our treatment to be doing better than our control at any given point in time. Okay. Hazard is going to represent an instantaneous event rate, and that means the probability that an individual would experience an event like death, relapse, promotion, right, at any particular given point in time after the intervention was done. And that's assuming this individual survived to that particular point without, because, they can only have the event once if it's death, right? So, and like I said, I'm not going to go into the math today, but you will get hazard ratios and they will be delivered in your output, and they have confidence intervals too, which is great. While a hazard ratio is similar to a relative risk ratio, it isn't exactly the same. An example would say, let's say a clinical trial investigated survival rates for 2 drugs, drug A and drug B. The reported hazard ratio and relative risk ratios are both 2. So the relative risk ratio is going to tell me that the risk of death is 2 times higher with drug A than with drug B over the entire study. It's cumulative, so it's all the study, everything all together. But you're not really looking till the end of the study. But a hazard ratio is going to tell you that the risk of death is 2 times higher with drug A than with drug B at any particular point in time. Okay, so and there's something called proportional hazards and such that I'm not going to go into today, but that is a term you can look up, and that's an assumption you make when you do these analyses, that your things aren't going to change mid-trial. Like a big problem might be that somebody we have cancer groups and we're looking at survival rates in different stages, but then there's a new way of testing to see what stage they're in that's more accurate, and it changes your groups around. You don't want to do that. You want to make it so that the treatment stays the same throughout, and that we're everybody's going to kind of stay the same. Now, of course, if you're in a treatment group, things might change over time, of course, because that drug might not start right away, or a surgery. Maybe somebody had a surgery and you might have some people fall off early on, but then they improve. The ones that survive improve. So, but you definitely want your control group. You don't want anything going wrong with that, right? Those are controls. They're supposed to have some kind of proportional hazard throughout. Let's go on. I'm going to go on to the next little thing here. I thought it might just be better to show a picture. Here's what you would get in your output with your hazard ratio. This is hazard ratio for death in the treatment group, okay? And then this was a hypothetical study, okay? And I got it from here. It was a very nice, if you want to read about the study, and they'll tell you more about hazards. It was the hypothetical study was a randomized controlled trial, investigated the effectiveness of a new treatment for improving the survival of patients with heart failure. Okay, so a total of 105 patients were treated, and they were randomized into the treatment group, and 106 were randomized into the control group, and the primary outcome was overall survival. Okay, so the main result of this trial can be summarized in a paragraph. Okay, you can basically say after a medium follow-up of 1,500 days, the hazard ratio for death in the treatment group, which was 0.038, and it has this 95% confidence interval. So we are 95% confident that the true ratio is somewhere inside here. Okay, it was 0.38 and had this p-value. Okay, so it means that the patients in the new treatment group at any point of time during the study period were 62% likely to die, because you take 1 and you subtract that 0.38. Okay, so they were 62% less likely to die than patients in the control group at any given time in the study. And we're 95% confident that the true value is somewhere between 47% and 72%, because we also subtracted both of these from 1. Okay, so that's pretty good. Yeah, so we can be 95% sure that patients in the new treatment group were between 47% and 72% less likely to die than patients in the control group. So let's look at this curve. It's a Kaplan-Meier curve. It's a graphical method of displaying survival data, also called time to event data. It's the proportion of patients surviving against time. And it's typically a step function. So up here, everybody's alive at the beginning. Okay. Down here, I should show you the x-axis is time. Okay. So this is going to be, I think, months, because it's days. Okay. So yeah, 3,650 divided by 10. Yeah, so these are days. Okay, so at the beginning of 0 days, everybody's alive. Okay, and then the first event happened down here. Okay, the y-axis is the patients surviving. Okay, so at 0 days, everybody was alive. Okay, and then we go down over time. This is the control group. These are the ones that didn't have the treatment, the green line, and you can see they go down much, much faster. Okay, and here is the treatment group. Okay, and they're going down much slower. Okay, and by the end of the study, our treatment group, we had only lost maybe 30%. We were down to 30% surviving, but the control group, my gosh, we were way down here, maybe 5-10% surviving. Big difference at the end of the study, and all throughout the study, right? Each of these little ticks is a censored observation, so these people were still alive. What they did, they looked right here. This is when they did the hazard ratio in the test. This is when they did the analysis at the 10-year mark. Okay, these people were continued to follow up after, and they're fine. So they didn't die by the end of the study. Okay, I guess we could look at median survival right here. The treatment group median survival. Half the patients in the treatment group survived for about here's the 50. The treatment group, they survived about 22,246 days. Half of them, median survival, survived. Half of them survived then. And then for the control group, median survival was way back here at 906 days. So, half of the control group were gone by 906 days, but half of the treatment group, they were gone by 20, much longer. Okay, so you can find a lot of things from the time. So you can do your difference in median survival then. So on average, patients in the intervention group and the treatment group, they survive for about 1,340 days longer. So you take this number and subtract that number, and it tells you how much longer the treatment group survived for median survival. Likelihood ratio. This is the one that made me do this seminar or this webinar, because in the Bayesian logic, if you go back, it's there. If you go back and listen to it on the YouTube channel, it's free. You can go back and listen to it. a couple months ago. I was trying just to show how to do the little likelihood ratios and figure some computations, and it was just a little formula, but everybody had so many questions on that. And I actually had some trouble answering the questions. And one of the big questions was, well, what does that mean, like probability wise? What does that mean in a way I can understand? And so I looked into it a little bit more, and I was mentioning in the webinar that it's not all that easy to do. It's not all that hard either. I'm going to show you a simple thing today. Again, I'm not the total end-all be-all expert in likelihood ratios, but it helped me learn a little bit more, at least on how to explain it to you. So hopefully I do better this time. Okay. So the likelihood ratio of any clinical finding is going to be the probability of that finding in patients with the disease divided by the probability of that same finding in patients without the disease. Okay, so here's our formula. On the numerator is the probability of the finding in patients who have the disease. And here's the probability of the finding in patients without it. Okay, and it's a simple little ratio. They're mainly used in diagnostic testing, but due to the computational effort needed to interpret them into easily understandable information, they are rarely used. This diagram here on the right is called a nomogram, or it's also called a nomograph. Either way, it's a tool that clinicians use. Nurses use it and such, and other clinicians in settings where they're hospital settings quite often. And they use it, not this particular one, but they will use one similar to it to decipher likelihood ratios without doing calculator work. Okay, so sometimes it'll be in the chart, and it'll be at the foot of the bed in the chart. The nomogram will be there, and they'll go, okay, I got this number for my likelihood ratio, and I'm going to match it up. Okay, and get the number I need so I can make more sense out of it. So it consists of a set of a few different scales, in this case 3 different scales. Okay, and so one scale for each variable in the equation. So typical of equations, in this case, if you have 3 things that you need to know, there's 3 numbers, and you know 2 of them, you can figure out the other one. Okay, that's math. If you know 2 variables, you know the values of 2 variables, or two things in an equation of 3 things, you can figure out the third one. Okay, so that's algebra. Okay, so knowing the value of all but one, the value of the unknown variable can be found. Or you can fix some of the variables. For relationship between the unfixed ones can be studied. Okay, so the result's going to be attained by you lay a straight edge or a ruler, or maybe the nurse takes her pen, or whatever she has, and across the known values, and then that'll give you the answer that you need of the other one. So this picture here calculates a value of t. Okay, when we have s at 7.3, so here's our s scale. And so we know S is 7.3, we know R is 1.7. So what we'll do is we'll take our straight edge or our ruler, and we'll put it on the 7.3 here, and we'll put it on to the 1.17 here, and then we can go and look here, and we can go, okay, well then my T is right around, it's just under about a 4.65. Okay, so it kind of gives you an idea right there. So you can do that, and it'll help you find. So a lot of times that's how these work. Okay, and they'll use these they'll do it with likelihood ratios. I couldn't find one for a likelihood ratio, so but it's the same kind of technique. Okay, so likelihood ratio can range from 0 to infinity. Okay, if your likelihood ratio is between 0 and 1, that argues against the presence of the disease or the condition. Values closer to 0 are associated with less likelihood of that condition, of having that condition. If you have a likelihood ratio that equals 1, it lacks diagnostic value. You can't really tell much about it. Okay, if it's equal to 1, it's not telling us anything. If it's greater than 1, then that's more convincing that the finding that you have suggests the presence of a disease or condition. Greater numbers are more convincing, and I'll show you an example. So again, we're going to have this example. It's from McGee. I have it in a reference list. His article's free online. He actually has a table that he made to help convert likelihood ratios to probability. So and his articles is selling that, basically this is great, you should use this. You can read a little bit more about this study and a little bit more about likelihood ratios themselves, but it's very interesting. So there's patients have abdominal distension, okay, and they undergo ultrasound, okay, but there's physical signs maybe that can be used to kind of see if a person has a disease. One of the and what we're looking for is looking to see if people have ascites, okay, and ascites is when you have fluid that builds up in your stomach cavity, right here. It's in your peritoneal cavity. It's in your abdomen. Okay, so it's like right here between your diaphragm, and it's right in here. And so some people will get they'll get very bloated. Okay, so you can take a sonogram, right, and you can kind of see if there's fluid in there or not. But sometimes there's visual signs that maybe a nurse at bedside can try to maybe see, diagnose if maybe they do have the ascites. So one of them is that they'll look for bulging flanks. Okay, bulging flanks is whenever you have you can kind of see on the side that there's some bulging coming out on the side. Okay, or they can do a tympany, and tympany is when they're gonna thump it like it's like thumping a watermelon, right? And if it's a hollow sound, that's probably gas. Okay, and not water or fluid. Okay, because gas might just be gas. It's no big deal. But if it's water, they're retaining water in there, then that might be a problem. Okay. So we know that among patients that have that abdominal distension who undergo the ultrasound, the physical sign of bulging flanks is going to be present in 80% of them who have the confirmed ascites. Okay, so 80% who have bulging flanks and have it confirmed by ultrasound. If they have bulging flanks and they get it confirmed by ultrasound, they're going to have the ascites, 80% of them, okay? And in 40% without ascites, they're still going to have the bulging flanks, but it could be just because of the gas or just distension for some other reason, okay? So the likelihood ratio for the bulging flanks in detecting ascites, therefore, is going to be 2, okay? Because what we're going to do is we're going to take the 0.80 and we're going to divide it by the 0.40, and that's going to give us a likelihood ratio of 2, okay? Similarly, if the finding of the tympany is present, it's present in 10% of the people that have the ascites, but 30% with distension from other causes. Okay, and that makes sense because if it's sounding hollow, that's gas, right? Because if it's filled, it won't sound hollow. Okay, so but it's not as good of a measure for detecting it, right? It seems like bulging flanks. It seems like it'd be much more informative. However, we're going to get a likelihood ratio for that. So we're going to take the 10% of the patients that have it with the tympany, okay, and then 30% with distension from other causes, okay. So these are our 2 likelihood ratios. So now we can take this information and go, okay, well, big deal. A likelihood ratio of 2 and a likelihood ratio of 0.3. What does that really mean? And this is kind of what we came across in the last webinar. So the questions would be, how much does the finding of bulging flanks argue for somebody having, ascites? And how much does the finding of the flank tympany, which is this likelihood, argue against it, right? Because remember, it's forward if it's above 1 and against it if it's less. So there's some steps we're going to do. And they're not that hard once you start looking at it. We're going to determine the pretest probability, and that's going to be the prevalence of the condition, okay? Then we're going to convert that. We're going to take the pretest probability, and we're going to convert it to pretest odds. Then we're going to multiply those pretest odds by the likelihood, and to derive, and then we're going to get, and that's going to give us a post-test odds. And then we're going to take the post-test odds and we're going to convert them back. Okay, now back to a probability. Okay, and that's going to give us a number that we're going to go, okay, that makes much more sense to me. And this is why it's a little bit computationally intensive, why it's hard to do bedside, and why you want to have those little nomograms or maybe the table that McGee talks about. Okay, so let's do them one at a time. How much does the finding of bulging flanks with a likelihood ratio of 2 argue for ascites? Well, first we're going to determine that pretest probability, which is prevalence. We're going to get that from research. We're going to get that maybe we might have a sample, or we did the ultrasound, so we kind of have an idea of that, But we're going to show that the prevalence of ascites in the population is about 40%. Okay, so this we can't find out from the computations. We have to get it from the literature or something we know, okay? This is where it's Bayesian again, right? Because we're coming in with some information we know. We're going to use it for our calculations. Then we're going to convert it. We're going to convert it from the pre-test probability to the post-test odds. So here we want to find the odds, the pre-test odds. So we're going to take our pre-test probability and divide it by 1 minus the pre-test probability. So we're having our 0.4, 1 minus 0.4, we get this number. Okay. Now we're going to multiply the pre-test odds, which is this 0.667, by the likelihood ratio, and then we're going to get this number, 1.334. Okay. Now we're going to convert it back. When we want to go back to the post-test probability. So we're going to take our post-test odds, which is this number, the 1.334, and we're just going to divide it by 1 plus that number. Okay, we come up with a 0.57. We multiply it by 100. We get 57%. Thus, having bulging flanks increases the probability of having ascites from 40%, which is known in the population, to 57%. So if you could diagnose them with that bulging flanks, you're probably going to increase the probability of having it from this to this. Much nicer, okay? And you can do the same thing arguing against. It's the same computations. I won't go through them all, but it's the same computations. And so if you have tympany, that's going to decrease the probability of having ascites from 40% to 17%. Okay, so you can look at it both ways, but there's how you convert using the likelihood ratios. You can go from pre-test probability to the post-test probability to see, what are the chances. Here it went down, which is good. Okay, so here's some references. Here's the McGee reference about the likelihood ratios. Bland-Altman, a lot of the ratios we looked at today, they are responsible for. The Kaplan-Meier curves, I think there was another one, I can't remember, was it the risk ratio? They're in a lot of things, okay? Penn State has some great statistical information. And then here's something about how to read a Kaplan-Meier survival plot that might be useful. And I want to thank you. And we did go over a little bit. I'll try to go faster next time, but I think all the information was very good, hopefully helpful. I hope it was. And so if anybody's still here, we can ask some questions, maybe for 5 or 10 minutes. And then I'll let you guys go. And if there's any remaining questions, I have them here. So type them in, and I'll try to get to them later. Okay, Jerry asked what was actually being inflated with the variance inflation factor. Well, I guess variance is actually being inflated. I would have to look that up myself to see the exact formulas for it. I can look at it and see what it means, but when you get away from math, we really concentrate on math a lot in school. But I'm an applied statistician, so I kind of moved away from the theory. And I still do math and such, but as far as the exact, sitting there running calculus, I'd rather not. But I'll look it up, and I can do it if I need to. But it does. It's inflating the variance. It's inflating it so that probably because the R squared is based on variability. So it would be something that's going to make that multicollinearity might be inflating some of the variability in the outcome. So that's about the best I can say with that. Does risk imply the passage of time? Not in the way that we looked at it. Risk is implying just risk. It's not risk over time would be the hazards ratio. It looks like this question was asked a little bit earlier, so maybe that got answered. But it's actually risk, and the risk ratio is done after a study. So it's after the time of the study, but it's just after the study. We didn't take into account time. Jerry wanted to know if there was an app for something, and I'm not sure what there would be. If you can ask me again, an app for what, Jerry, and I can let you know if there's an app. Let's see. Would you show the references for likelihood ratio again? Yes. This one right here, McGee. Okay. Well, thank you. Thank you all for coming. This is very, very nice. You have my email. It's on one of these slides, I'm sure. If it isn't, it better be. Yeah, you can, if you come up with if you're looking at it later and you come up with a question and, it's like, darn, I didn't ask that, or now I need to ask this, email me. Okay, here's my email right here, and I'll try my best to get back with you and let you know, or send you a reference or something like that. Because I always say, if you're on my mailing list and you're coming to my webinars, you're my peeps. I'm going to try to take care of you, right? So if it's something big and major and a project, of course, we'll discuss fees. But if it's an easy answer or an easy reference, I'm always happy to give it. Okay, so I want to thank you for all coming and sticking around. And this is a great. I'm very happy with this. I'm pleased with myself. And thank you for the delays, for your patience with that in getting this done. And I hope to see you guys in November. And have a great weekend. And have a good afternoon. Bye.